our work on the image-based and automatic prediction of fresh concrete properties from concrete flow. Fresh concrete is usually in practice characterized by its workability, a term which comprises usually the consistency of the concrete, but is also of course related to the rheology of the concrete. And the workability is important or a significant factor for incorporation of the concrete, as an improper workability can lead to segregation effects or air voids and ultimately to damages in the building component. So current test methods are, for example, the slump flow test, in which the concrete is spread on a standardized table and the diameter is correlated to the consistency class, or rheometer tests, which are more like laboratory tests and not so much practiced on the construction site. And both of these test methods are batch-based, empirical, sometimes even subjective, and as I said, impractical on the construction site. So what we therefore propose in our work is to measure and predict the workability of the concrete directly at the delivery by observing the concrete flow flowing at the discharge of the mixing truck. And for this we installed cameras on top of the concrete channel, observing the concrete flow, and by computing the motion of the concrete, we assume that we have all the relevant information that we need to predict or derive the fresh concrete properties from this information. So more formally, we know from fluid dynamic laws or fluid dynamic models that the flow is a function of the properties of the fresh concrete. In this case, we represent it by the state vector, which comprises the plastic viscosity and the Bingham yield stress, so the rheological properties and also the slump flow diameter, and of course of the boundary conditions. And in our paper, we tried to solve the inverse problem, namely to determine the fresh concrete properties from observations of the flow behavior. And to this end, we tried to find a mapping function in form of a deep learning model, for which we used the vision transformer in this work. So from a high-level overview, this is our setting. We have our acquisition setup at the discharge channel of a mixing vehicle, and the input to our approach are image sequences, so a temporal sequence of acquired images from the flow. And we feed this into what we call concrete flow transformer, which is kind of a vision transformer architecture with a goal to train it and predict the rheology and the consistency of the fresh concrete. So, as I said, as input, the image sequence is used. And in the first step, we compute the optical flow, so the pixel-wise motion between one frame and the subsequent frame. And in this information, of course, the flow behavior of the concrete is represented. And now, assuming that in the flowing direction, we have a constant flow in each image line, which means we have redundant information in flowing direction, we decided to only cut out a slice of the dense optical flow maps and use these as flow tokens, which are then used as input to the transformer architecture. So they're linearly projected, and we create the flow tokens from them. And as a standard for regression or classification problems, we add a learnable class token to the sequence, and the whole sequence of tokens is then fed to the transformer encoder. And we implemented a multitask head on top of the encoder, one regression head which predicts the real values for rheology, so the viscosity and yield stress, and a classification head which predicts the consistency class of the concrete. To test this approach, we went to the construction site and built a real channel equipped with a sensor, the channel with a fixed size and a fixed slope to have constant boundary conditions. And we acquired a quite huge data set comprising of several concretes with several or different reference values. We used the slump flow table test and the concrete rheometer to acquire reference values. And as we can see here, we have a broad coverage of the concretes with the target parameters. Yeah, so let's have a look in some quantitative results. So the first thing that we predicted is the slump flow diameter. And as we can see here in the table, we achieved in the prediction mean absolute error of 2.3 centimeters with a quite huge standard deviation of 3.4 centimeters. Sorry. And in the graph below, we can see the reference curve, which is the green line, and we can see the distribution of data samples around the line. And we can see that especially at the boundary cases of the parameter range, so in the upper and lower boundary, we have the largest error range, which we think comes from the long tail problem, that we have a lesser dense coverage of these parameters in the training data set. Related to the slump flow diameter is the consistency class, which is predicted by the classification net, and the consistency classes of the concretes were predicted with an overall accuracy of 77.4%. And as we can see in the confusion matrix, which is shown here on the bottom right, most of the confused, so erroneous predicted classes are lying in the neighboring classes of the true class. So when there's an error, it's very likely that the error belongs to one of the neighboring classes, which is quite an interesting observation. And of course, the same we did also for the prediction of the rheological parameters. We see here the mean absolute error of the yield stress and the Bingham fluid. And also in the graphs, we show the reference line, and we see that the predicted values are quite close and very precisely reconstructed from the reference values. So to conclude, we presented an image-based method for the fresh concrete characterization and quality control, which is applicable on the construction side, and which has the advantage that not only a batch-based quality performance is done, but in theory, every liter of the concrete brought to the construction site could be tested. And we presented the concrete flow transformer, especially our proposal of flow tokenization, and achieved promising prediction results for both the consistency and also the rheological parameters. So in the future work, we aim at not only apply this method at the delivery, but also during production in the concrete plant, where we plan to install cameras in the concrete mixer already to determine the fresh concrete properties there, in order to obtain the capability to adjust the mixture in real time during production. So with this slide, I would like to end my talk, and I'm happy to answer questions or lead a discussion here.